In this video, we're going to talk about hypothesis testing. Now, in many ways, we've been building up to the idea of hypothesis testing since the beginning of the course. And in this video, I'm going to talk about the very logic of hypothesis testing and then walk through a specific example of how you would perform a hypothesis test using the z-first sample mean. In this example, we're going to say that we have a population of 6th graders, and when they take a standardized reading comprehension test, the average of the entire population on that test is a score of 80, and the standard deviation is 10. Now, in this example, we're going to say that someone has developed a new way of improving reading comprehension, a new treatment in some way. And they want to know if this treatment works or not. Well, obviously, it'd be too costly or too time-consuming to study the entire population. So instead, they take a sample. And we're going to say that this sample has a sample size of n equals 100 people. And so every single one of these 100 people is going to get this treatment. In order for you to understand the logic of hypothesis testing, you have to think about this question. In this example, what score do you think this sample would give on this test, this sample of 100 people? What score would they get on the test if the treatment did not work at all? What do you expect them to get? That's as if the treatment does not work. If it didn't work, you would expect them to give you a score of 80 because that's what the population mean is. We took a fairly large sample, and if the treatment doesn't work, we'd expect that sample mean to be the same as the population mean. What if the treatment did work? We would expect the scores to go up, right? The treatment should increase reading comprehension. We don't want to use it if it actually hurts reading comprehension. We'd expect it to go up. But how much does it have to go up in order to be convincing evidence that the treatment actually worked? For example, let's suppose that we do this study just as I've described, and the mean gives us, the sample gives us a mean of 82. It's higher than what we would have expected, 80, but is the difference between 82 and the population parameter of 80, is that difference possibly due to sampling error? Or is it due to the treatment? These are the two possibilities that we have to deal with when we're dealing with hypothesis testing. The first is that the change between the sample statistic and the population parameter, this increase of 2, is this increase of 2 caused by the treatment working? Or is this difference between 82 and 80 due to sampling error? This is the question that we're trying to answer with the hypothesis test. And the way we're going to do it is we're going to calculate the probability that the 82 was created by sampling error. We're going to come up with a probability, a p-value, and if that p-value, that probability is very, very low, then we're going to say that it's probably not sampling error, and it's probably caused by the treatment. Let me say that again. We're going to compute a probability that the 82, the difference between the 82 and the 80, was created by sampling error. And if that probability is very low, we're going to say that the difference was not created by sampling error. We're going to say it was created by the treatment. That's the basic logic of hypothesis testing. Now let's go through an example. We're going to use the same example, the same parameters that we used before. The first step in hypothesis testing is to state the null hypothesis. The null, in this case, is going to be, what we're saying is the mean of the treatment, that's what this mu sub t means. The mean of the population, if we were to give everyone in the population the treatment, that's what the T stands for. The mean of the population, if we were going to give everyone in the population the treatment, is going to be less than or equal to 80. That means that the null hypothesis is saying that the treatment does not work. The null hypothesis is saying that any differences that occur in our study were created by sampling error. So that 82, that 82, the null hypothesis is saying that 82 was created by sampling error. We know that it's greater than 80, but we're saying it's not really caused by the treatment. It's really caused by sampling error. The research hypothesis is saying the opposite. The research hypothesis is saying that the mean of the treatment is going to be greater than 80. And so the real difference, or that difference, is really created by the treatment working. Those are the two possibilities. The mean of the population, if we treated everybody, is going to be less than or equal to 80. Or the mean of the population, if we treated everybody, is going to be greater than 80. Remember, in our study, we only used a sample, not the entire population. That's why even though we have an 82, and that's obviously above 80, that difference might be created by sampling error because we used a sample. Okay. Next step, we need to find the critical region. So what I've drawn here is a distribution of sample means with the z-score number line drawn in. The next thing we want to do is we want to identify the cut line on this distribution that identifies the 5% of the curve that is designated by the alpha value. The alpha value is telling it how small does that probability have to be in order for us to reject the idea that it's due to sampling error. Remember how we started at the beginning? We're going to compute a probability that a given result is due to sampling error. How small does that probability have to be? Well, that's determined by alpha, and that's determined before you start the study. In this case, the alpha value of 0.05 says if we get a probability for sampling error that's less than 5%, we're going to reject the null. And so we have to find what that number is. We need to find the z-score that corresponds to a probability of 5% or less. The way we do that is we use appendix in the back of the book, and in the tail column in appendix A, we go down till we find 0.05. And then we go, once we find that in the tail column, we're working from the inside of the table out. So you find 0.05, or the closest you can to it, and then you find the z that is on that line, and then that will give you the cut line for the z value. If you do that, you're going to find that the value that you get is 1.65, and that is 5% of the curve right there, 1.65. That means basically if we get a z-score that is on this side of this line, we are going to reject the null hypothesis. If we get something on this side of the line, we're going to not reject or fail to reject the null hypothesis. We're going to say, if we get something on this side, we're going to say it's due to sampling error. If we get something on this side, we're going to say the probability of it being sampling error is small. It's less than 5%. So it's probably not due to sampling error. It's probably due to the treatment. Okay? Now we actually have to compute the statistic. Here are all the known values from the previous page. the example. We're going to use this equation because we're dealing with a sample mean. We're essentially asking, what's the probability of getting a sample mean of 82 when you have a sample of 100 people? And the standard deviation is 10. So we take all those numbers and plug it in, run through the math, and we find that we get a z-score of 2. Here is the distribution of sample means from the previous page with the critical value of 1.65. And now we locate our obtained z-score in this curve, which is right here at 2. And obviously that is in the critical region. It is on this side of that line. And so it's unlikely that we would find a z-score of 2 in this situation. It's going to happen less than 5% of the time. So it's probably not due to sampling error. It's probably because the treatment worked. The next step is to compute the effect size. We use this equation. We plug in the numbers, do the math, and we get a 0.2. And then we always use these cut lines to interpret the D. We got a 0.2 exactly, so that means that this is a small effect. We rejected the null, right? On the previous page, we rejected the null, and that says that the treatment worked. The next question, and that is answered by effect size, is how well did it work? Well, we got a 0.2, which is a small effect. That means it didn't work really, really well. It had a small effect. It wasn't extremely effective, but it did do some good. The next step is to summarize the results in an APA format of a result. Now, there's lots of ways of doing it. Basically, what you have to do is write a complete sentence that just says what the result was. Did the sample mean come out to be significantly higher than the population mean? So you simply need to write a sentence about the result. Here's one way you might do it. Those getting the treatment had a higher reading comprehension score than those in the population. And then we've got a bunch of what I call stat stuff, right? You put Z because you ran a Z test. You always put the sample size in parentheses when you run a Z. So N was 100. Again, telling people that your sample size had 100 people gives them some idea of how large your study was and really how trustworthy your results were. 2 is the obtained Z-score that we got. We write P less than 0.05 because the critical value of 2 was in the critical region, or excuse me, not the critical value, the obtained value of 2 was in the critical region. So we reject the null. Anytime you reject the null, you're going to write P less than 0.05, and then you write D. All right, so this is a full example of how you would run a hypothesis test using the Z for the sample mean.